Imagine standing at the edge of a lake. The water is still. The shoreline drops away sharply on all sides. You can see the bottom, but only barely, because the depth here surprises you. Now imagine that the lake you are standing beside is not sitting in a valley carved by ancient glaciers, not nestled in a mountain range, not fed by rivers or rain in the conventional sense. Imagine instead that the water surrounding this lake is not air at all. It is ocean, and the lake itself sits on the seafloor, motionless, bounded by its own chemistry, behaving by rules that feel like they belong to a different world entirely. That is the premise behind one of the ocean's most disorienting phenomena. Lakes that exist beneath the sea. Not metaphors, not approximations. Actual bodies of water pooled inside the ocean with their own surfaces, their own shorelines, and in some cases their own weather. To understand how something like this can exist at all, you have to start somewhere more familiar. You have to start with what a lake actually is and what makes one body of water separate from another. Consider Hidden Lake on Alaska's Kenai Peninsula. It sits inside the Kenai National Wildlife Refuge, formed from an ancient channel of the Kenai River. The lake reaches depths of up to 148 feet, roughly 45 meters, at its southeast end. Its northwest backcountry section is shallower, ranging between 10 and 70 feet. The shoreline is steep and wooded with birch and spruce. Its only outflow is a short, shallow creek that feeds back into the Kenai River just north of Ski Lac Lake. What makes this a lake, and not simply part of the river system it borders, is separation. The chemistry is different, the movement is different. The depth and containment create a distinct body with its own identity. The boundary is physical, geographic, and hydrological all at once. Now carry that logic downward. Carry it thousands of feet below the ocean's surface into pressure that would crush unprotected equipment and temperatures that hover just above freezing. What could possibly create a boundary there? What could separate one body of water from the ocean, pressing in around it on all sides? The answer is density. And density in the deep ocean is shaped by things that do not behave the way surface water behaves. Think about the glacial tarns in Nevada's Ruby Mountains. The hidden lakes there sit on a shelf above Soldier Basin at an elevation of roughly 9,500 feet, nearly 2,900 meters. They are small, covering about 9 combined acres, and they reach depths of only 32 feet. But they persist as distinct lakes because they occupy a specific position, bounded by topography, fed by snowmelt, draining into Soldier Creek and eventually the Humboldt River. Elevation, geology, and hydrology conspire to hold them in place. Beneath the sea, the conspiracy is chemical rather than topographic. When water in the deep ocean becomes extraordinarily dense, denser than the water above it by a significant margin, it stops mixing. It settles. It pools into depressions in the seafloor. It develops a surface. And from that surface, in certain conditions, waves have been observed to form and propagate, just as they do on the lakes you know. The lakes in Montana's Gallatin Range, that series of 8 lakes on the west slope of the Gallatin Range in Gallatin County, sit at an elevation of 9,025 feet, or about 2,751 meters. They are located at the head of Hidden Creek, a tributary of Portal Creek, east of Windy Pass and south-southeast of Garnet Mountain. They exist because the mountain holds them. The terrain defines their edges. In the deep sea, the terrain still matters, but it works differently. Basins and depressions on the ocean floor become vessels. The dense water fills them and cannot rise, because the water above is less dense, and the physics of buoyancy holds the boundary in place with a precision that rivals any physical dam. The result is a surface, a real interface between two bodies of water with different properties. Scientists have sent vehicles down to that interface and observed it behaving like a lake surface behaves. Objects moving across it create disturbances. The boundary ripples. Below the boundary, conditions change sharply. What lives near that boundary? What chemical processes sustain themselves there? And how the deep sea environment is structured around such features remain active areas of scientific investigation. Instruments capable of surviving those pressures and resolving those boundaries have only existed for a relatively short span of time. Much of what is known about these features comes from expeditions that could not have occurred even a few decades earlier. The limits of that instrumentation matter. An ROV descending toward a deep-sea pool carries sensors that were calibrated for a range of expected conditions. When those conditions lie near the edge of the instrument's design envelope, the measurements carry uncertainty. A reading near the boundary of a dense pool is not the same as a reading well within it. The difference matters scientifically, but the difference is sometimes hard to characterize with precision. This is the honest position of deep ocean science. Not that we know nothing, but that what we know is bounded by what we have been able to reach, sample, and image. The ocean is not unknowable. It is simply large, deep, and resistant to the instruments we have built so far. The best current understanding of these submerged lakes treats them as real physical features governed by density stratification, seafloor topography, and chemical composition. They are not anomalies in the sense of violations of physical law. They are what physical law produces when the right conditions converge at depth. Their strangeness is not a mystery of origin. It is a consequence of scale and of how rarely humans have had the tools to observe conditions that far below the surface. What remains unresolved is the full extent of their distribution, the precise boundaries of the ecosystems associated with them, and the degree to which conditions at those boundaries support life in ways that are not yet catalogued. Each expedition that has reached such features has returned with data that opened new questions alongside the ones it closed. The lakes in Montana, Alaska, and Nevada persist because geography holds them. They drain slowly, fill with snowmelt and rain, and maintain boundaries that have existed since the landscapes they occupy were shaped by ice and water over thousands of years. They are old, and they are still. The lakes at the bottom of the sea persist by a different logic, but they persist just as completely. Dense water held in place by the weight of the ocean above it does not drain in the way a mountain lake drains. It sits, it waits. It develops a chemistry and a character entirely its own. The question that a scientist standing at the edge of one of those deep features would ask is not how something this strange got here. The question is, what is happening at that surface right now, at this moment, in the dark and the pressure and the cold, where we have not yet looked closely enough to know? And adjacent to that question, quietly waiting, is another one. If density alone can create a lake inside the ocean, what other boundaries exist down there that we are only beginning to find instruments precise enough to detect? The ocean does not withhold its structure to confuse us. It simply operates at scales and under conditions that our tools are still learning to meet. That gap between what the ocean contains and what we are currently equipped to observe is not a failure. It is the frontier. It is the reason expeditions still descend. It is the reason the instruments keep improving. And it is the reason that what seems impossible at the surface turns out, at depth, to be simply physics doing what physics does in a place we have barely begun to know.